The question that I have is, could you illustrate the use of the principle of moments via an example? Let's go ahead and do this example. We have a force of 100 Newton is acting at this point on this little structural element. All right, the direction of the force is given in terms of the ratios, and this distance is 5 meters and this is 2 meters, and we want to find the moment of this force about point O. Let's go ahead and solve this problem by both methods, starting with method number 1, where we work from the definition of moments. So this method requires that we find the perpendicular distance, the line of action of the force, right? So this is the line of action of the force, and this is the perpendicular to it, and therefore we need to find this distance. So you can see it's not straightforward. So I did draw some construction lines here, which should help us find that distance. It seems like it's easy to work with angles than the ratios. So I'm going to call this angle as theta, and then this is 90 minus theta, this is theta, this is 90 minus theta, this is theta, right? So I went ahead and found theta first. So by just looking at this little triangle, you can see this is theta and this angle is theta, right? So tan theta is opposite side divided by the adjacent side. That will be 3 over 4. And therefore theta equals tan inverse of 3 over 4. That gives me a value of 36.9 degrees for theta. Now let's try to figure out how to find d, little d. And by looking at this geometry here, you can see d is this distance plus this distance, right? This distance plus this distance. But this distance can be found by considering this triangle, and this is 90 degrees, this is theta, this is 5 meters, right? And therefore this distance should be equal to 5 sine theta, right? And then I want to find this, which is exactly equal to this distance, right? And that distance can be found by considering this little triangle, and this is 2 meters, this is theta, this is 90 degrees, and therefore that should be equal to 2 cosine theta, right? So I add 5 sine theta to 2 cosine theta, that's my d. So I get a value of 4.6 meters for little d. And this force is going to give me a clockwise moment about point O, because it's rotating like this, right? And therefore I introduce a negative sign in front of the term, and the magnitude of the moment is force, which is 100 Newton multiplied by the perpendicular distance, which is 4.6 meters. So you get a value of minus 460 Newton meter for the moment of this force about point O. Alright, now let's go ahead and do this by our second method, which is to use the principle of moments. So the first step is to define a coordinate system. So this is the system that I have selected. Now why did I select the coordinate system like this? Well, it's primarily because the dimensions are given in two perpendicular directions, right? This is one of the directions, the other is this, right? And therefore, the calculations would be much easier if I select my coordinate system to be parallel to the direction in which the dimensions are given. The second step is to go ahead and resolve this force into components, right? One along the x-axis, the other along the y-axis, and find the magnitudes of these components. So this part right here is 100 multiplied by 3 over 5. So 3 over 5 will give me the vertical component, right? So that's what I have over here. And the horizontal component is 100 multiplied by 4 over 5. 4 over 5, right? Our third step is to go ahead and sum up the moments of individual components, right, in accordance with our sign convention. So our sign convention is this, and this part right here, the horizontal component, is going to give me a clockwise moment, and therefore I have a negative sign in front of that. So that's the force, 100 times 4 over 5, right? And the distance is 2 meters. Why? Because this is the line of action of that force, and this will be the perpendicular distance, right? So this distance is exactly equal to 2 meters, so we have 2 there. And the y component is it's a force going down, and it's also going to give me a clockwise moment, therefore I have a negative sign in front of that. And the magnitude of the moment is force, which is 100 times 3 over 5, multiplied by the perpendicular distance, which is 5 meters. Why? Because this is the line of action, right? The vertical line passing through that point. And this is the perpendicular distance to that, right? So that's 5 meters. So that simplifies to 460 Newton meter minus 460 Newton meter, which is exactly what we got by method number 1. But you can see this method is a lot easier than method number 1 because we don't have to do all those constructions and try to figure out this perpendicular distance, which is not that straightforward.